Okay. So people who are just setting up the VPNs, yeah, let's after the class also we can, some of you can come to me and I can help you guys out. Uh, so before I jump to the dropout, I mean we are only left for one part. Okay, understanding dropout, understanding batch normalization, and understanding data augmentation. Not too difficult, but it'll take 5 minutes each or 10 minutes each. So before that, I just wanted to kind of click on that link which I skipped on the um, in the first part. This is just a way to understand like what's going on. Like if you really want some good intuition on uh, what's going on. Actually, yeah, doesn't work. Okay, works. So this is a cool animation by somebody at Ryerson University. Uh, so this is the starting image. Okay, and actually the first layer has 5 filters. Okay, so uh, this is just showing like, okay, so it has, oh sorry, 6 filters, 1 2 3 4 5 6 filters, and it's just showing like, okay, if a filter is trying to output, so this is the output of one of the filters. Okay, so the filter is moving through this input tensor. In this case it's not really probably a tensor, but anyway, this is an animation. So it's moving from left to right, and the number computed here is from these numbers in the input tensor. That's all. So that's all I mean. So this neuron here, this output, this is a neuron here, right? So this neuron's receptor field is just this part. Okay, that's all this image is showing. And as you move from there to like left, you're scrolling to the left, and then similarly to the bottom and so on. That's what the computation of the filter is. Okay, it's just matrix multiplication. Actually, element-wise multiplication, not really matrix multiplication. Um, and then the next smaller ones are just max pooling. So they're just shrinking this dimension of whatever it is, 100 cross 100 to 50 cross 50, for example. It's just the average of the first 4 numbers, average of the next 4 numbers, average of the next 4 numbers. That's what this layer is doing. Okay. And similarly, next, now this is max pooled. Now again, there are filters here. Okay, the filters are pre-trained, so we're just seeing one bunch of activations going on from one input image all the way to the scores. Okay, so actually this is for MNIST. So the trained thing is for MNIST. So you can see that here's here in this case there are, I don't know how many filters there are. Um, 4, 4, 4, 16 filters, right? So there are 16 filters there. So actually there should not be 4, but so the animation is not that good, but it should. So this should take inputs from this part, this part, this part, this part, and this part, and this part. Okay. So there should be arrows everywhere. So this filter, okay, is taking the whole thing, this part of the image, and computing one number, and then again max pool. And then this architecture has only two things. Okay, one CNN, one max pool, CNN max pool, and then there are two fully connected layers. Okay, and then on the last fully connected layer, there's 10 classes. MNIST is a 10 image, what is it? Digit recognition data set. So you have 10 classes, 0 to 9, and so you can see that the 4 one is blue, which means that it has a higher score than the remaining. Okay, so just a animation for this. Actually, I think last time I mentioned try playground or tensorflow.org as well. That also essentially does something like this. Okay, yeah.
Let me get this up. Is there any like best practice for how small you want that last pixel layer to get before you put it connected layers as you can reduce the dimensionality? Like, is it obviously to make it too small, it's probably taken out all chance of getting anything useful.
Yes.
Like,
yes.
you don't want it too small or too big.
Yes. No, actually, if you see, I mean, most of the weights or the heaviness of the model is from these two fully connected layers. Okay. So the more filters you add at these layers is really not taking too much of in terms of there are very few parameters here. These two. Okay. There are a lot of parameters here because these are two fully connected. Literally, you can see that if it's 100 cross 100, there are already 100,000, no, 10,000 numbers there.
So it makes sense that you want to pull it down so that you're not fully connecting too many things, but you don't want to pull it down to one by one or 2 by 2.
You could pull it down one by one, but you need to, if you're using a lot of filters, then it'll be like a pooled, but it'll be a long array, right? I mean, see, pooling is just changing the spatial aspect. Like you can go down to one by one. That's sometimes fine, but there'll be a lot of filters typically. In fact, I think in the VGG one, that's what was happening. I think. Sorry, this. So you can see that here, it's actually 512 length depth. So the pool size, I don't remember how big it is. It's really pretty small. Okay, I think. Actually, you can check that. I think the images here were like 200 cross 200 or 256 cross 256. So you can see that 1, 2, 3, 4, 5. So if 256 is like 2 to the power 8, right? So 5 max pools is like divided by 2 to the power 5. Okay, so 2 to the power 3. So this max pool at the end is like 2 to the power 3 is 8, right? So 8 cross 8 is the dimensionality of the uh, width versus height. Okay, it's small. It's compared to like 256, which is a slightly bigger image. You only have an 8 cross 8 front facing, but then you have like 512 depth of this tensor, and then that whole thing is connected to like a 4096 fully connected layer. Okay, so most of the weights are actually here from actually between these two, because maybe from here actually, because this is 8 cross 8 cross 2 5 and 2, which is how much is it? So to the power 9 times to the power, yeah, to the power something. Okay, it's bigger than 4096, I think. Anyway, so most of the weights are over there, and all these guys, there's not much weights going on. Yeah, any questions? Yeah.
So one filter applies to only one input here, right?
One filter produces one activation map, and it applies to any input tensor of any depth. Okay, the filter depth is the same as the input depth. The one filter will produce one activation map at the output. So here, so when you write con 512, think of this as the output tensor, which has 512 filters, which 512 filters outputs are there, which means that 512 filters acted on their input and produced 512 such 2D slices. Okay, then they stack together, and that's the output tensor here.
So one filter amongst those 512
Yeah.
will operate on one input tensor, right?
The whole tensor is used to produce one 2D slice in the output tensor. Okay, because the filter depth is the same as the input depth, so it's not like when filter is just going spatially, numbers behind them are getting also getting multiplied, because the filter has a depth as well. When we slide a filter, it doesn't look like there's depth, but in the intermediate layers, the depth numbers also this one, the filter depth is not there, right? So actually filter depth is there. See, this filter, for example, I mean all the filters actually are supposed to, so this animation is not good, but so this filter, for example, not this filter, this filter's output, this is the output of a filter. At this, for example, at this point you understand, right? There are 6 filters. Okay, 6 filters, 2D outputs are here, right? So each filter is operating on this guy.
But there one filter is operating on 4.
Yeah, each filter, not just 4 actually, they should operate on all of them. That's what I said. The image is a little bit, it's not capturing arrows from here to here, but it should act on all the previous tensor slices. Okay, so here there are, I think 1, 2, 3, 4. Yeah, there are about 16 or 20 filters, right? Each filter is acting on the full depth of the previous tensor to produce one 2D slice. And since there are 20 filters, there are 20 slices here. Together, there will be like a 20 depth tensor there. Yeah. Okay. So we'll essentially, so there are some empirically validated techniques which are popular now, and I don't know, I can't guarantee that they'll be popular in the future. So it's something to learn for now, which are good in terms of like training CNNs, feedforward networks, as well as other much richer architectures as well. And they address 2 aspects of our classification pipeline, right? Data and models. Optimization and loss function criteria are also important. Actually, for example, localization should have a different loss function criteria, because you need to have bounding boxes in addition to class, right? And similarly, optimization, there are some schemes which work better, like Adagrad or Adam compared to SGD, but those are all things which are, I guess, orthogonal to the current issue. So we'll look at two things. One is data augmentation, a quite simple idea for images. Actually, it's kind of hard to do data augmentation for, I think, text and in general. If you have tabular data, it's kind of hard to do data augmentation. And uh, and on the model side, we look at model initialization is an important thing. Bash normalization would be an interesting trick, and then dropout. Okay, those are tricks to kind of get better trained CNNs, and also improve the training procedure itself sometimes. So let's start with data. So there are several questions you can ask about data. These are typical, so I'll not spend much time here. So let me directly jump into what augmentation means. So let's say you have, I mean, augmentation pictorially just means this. Let's say I have a data pair xi, yi, pass it through the input, get a loss function, and maybe get the gradient with respect to that data, li, loss with respect to that data point, right? Now, so instead of that, what I'll do is actually just slightly change the input feature vector to xi tilde, keep the label the same, and think of this as now a new data point. Okay, so maybe initially I had 100 observations. If I, for each one I create one more, then I have 200 observations. But the question is, how do I create x tilde I? Okay, that was not, as I said, that's not clear when you use tabular data or text data, but it's clear how to do this x tilde I when you have image data. And here's the visual representation. So let's say you want to classify this as a logo compared to say logos versus non-logos. Okay, then maybe, I mean, so let's say, so this is a example ith image, let's say a logo, and then it says logo as the class. You can change the colors, crop, flip, all these operations you can do, and all of them hopefully are also logos, right? So you can say that the class of all these guys is still a logo. So now instead of one input observation, you have like seven, three more, five more, like six in total observations. So you have increased your data size by six, but really not, they're not now independent data observations, right? They're all like the similar and perturbed versions of each other. In fact, there is a related idea called adversarial training, okay, which some of you may come across in like blog posts and so on. There also it's like saying that, oh, maybe for this image, because I have images like this, for these types of images, I'm able to train them as logos. But the moment I slightly change them to like some clip version like this, it says no, not logo. You don't want to do that. So maybe you can actually augment your data with perturbed versions to robustify your classifier. Okay, because images are like complicated objects, so they're not simple feature vectors. So data augmentation, is a way to create more robust classifiers, or also to actually get uh, more well-trained classifiers because you're increasing your data size. Okay. Any questions about what is it called? Augmentation. So there's actually in PyTorch or in Torch Vision, there are what I call transforms. Okay. So you can actually create these transforms. You'll see an example actually in that tutorial. In that tutorial itself, there is an example of doing this. In fact, in that tutorial, there's also an example of transfer learning. I just forgot to mention. So all the things that we are talking about today, okay, the tutorial that we started with in the beginning has these elements of these. So you should look into that. Um, so in PyTorch transforms are in Torch Vision, sorry, you can do transforms, jittering the colors, changing the colors, doing these flips and random crops and so on. Okay, and so you do that at training. At test time also, at test time you don't have to do anything, right? Why would you jitter your input? You can always at test time just get the input and say whether it's a logo or not. But you can also do a few things. Like for example, at test time you got an image, you can actually crop the image into parts and see if each part is classified as something. Okay, and then take a majority vote, for example. You can do those things. Okay, and I think in ResNet they rescale the image a few times, and then at each scale they get some different crops like this, and then each one is passed through. For each one you do a forward pass to figure out what the class is and then take a majority vote. Okay, so these are all tricks to kind of get a better sense of like given an input, get a better I guess more robust or more high confident output class. Okay, prediction. Yeah. So skip that. Okay. Now that was data augmentation. Simple idea. Now we'll look at two more ideas with a warm up being weight initialization. The two ideas are going to be batch normalization and dropout. Okay, so let's see. Um, so even before these aspects, I mean, there were questions on the forum as well as people asked like, how do you pick the nonlinearities? How do you pick the number of hidden layers? How do you pick the number of hidden nodes? Like, why filter size is this? Why stride that? Why zero padding? How many con layers? Right? Why con followed by pool? Why not two cons followed by pool? So there are lots of decisions that are already taken. Okay, so we are already like. Uh, quite a few decisions into it without too much of reasoning, except for like they seem to perform well. So similarly, there going to be some decisions that we'll take on some other aspects. Okay, which is, for example, the first thing is about actually not so much about the model itself, but about training the model, which is essentially the idea of weight initialization. Not really idea actually, concern. I mean, something that to keep in mind when you're training your network. And it's going to be critical when you train a network from scratch, which hopefully you will not do on the applied side. But if you're training network from scratch, it's extremely critical to initialize the starting weights or starting tensor values properly. So we saw that nn dot module with nn dot linear, right? So you want to start. You may also want to kind of specify what the weights are at the beginning in your neural network. Okay. For example, empirically people have seen that w is equal to 0 is a bad choice. Okay? Maybe because if you use if w's are zeros, then uh, your loss value could be something, but w's being zero influences like whether the local gradients are zero or not. Okay, depending on what nonlinearity you have and so on. So, so people do random initialization, and there are some names for these initializations, like Glorot initialization or Xavier initialization or something like that. I mean, there are a few like that, but they influence. Okay, and here's a simple picture. Basically, I mean, just to illustrate the point, like, like for example, if you want to minimize a function in one dimension, and if you start from initialize over here, you're getting the local optima or local minima, and if you initialize over here, you're getting the global minima. Okay. Even in one dimension, where do you start and do gradient descent influences where you get to? So you can imagine in a million dimensions, it's like a very very difficult process. Okay. Um, yeah. So I mean, that is just a thing about training. Now let's get to the architecture itself. Okay, there are going to be two tricks. First is batch normalization, and what is the motivation for batch normalization? So actually, so this is still an active topic. Okay, there are papers even this year asking about, oh, do we need batch normalization? Can we get rid of batch normalization and still get the same effect or not? And apparently, some papers saying that there's a lot of computation happening at batch normalization because there's some divisions happening as well. Typically, in the forward pass, you don't see divisions, but there's some divisions happening here. So anyway, it's still an active area of research. So at least the motivation, one motivation was that these activation magnitudes, right, ReLU's outputs, right, they're not very controlled. Of course, they are lower bounded by zero, right, but they are not. They can be large. Okay, they can be large, arbitrarily large. So and so you want to have some control on these activation statistics, because if they're large and then you're multiplying it with um, the next weight matrix, right? Next filter, maybe they're going to influence, and then if they're large and the weights have like the weight matrix has some negative values, then that the next value will be dead and so on. Okay, there is issues with things being too large or too small in general. Okay, and so uh, you know their values influence the gradient propagation. And in fact, this picture is more clear when you have a sigmoid nonlinearity, because if numbers are large, then remember the gradients there were zero and the sigmoid function, right? So there it's more clearer that if things are large, then you're kind of no gradients propagate. Okay, but for LO also there is a somewhat partial picture like that. And so what we want to do is control the size of these activations, okay, in the sense that we just want to post process the activations, right? So let's say con layer gave after relu operation gave me some numbers. I just want to post process, as in like just change those numbers to some smaller numbers and then pass it forward. Okay, so I want to introduce one more, essentially like a, I wouldn't call it a layer, but like a, or you can call it a layer, bash norm layer, which post processes the activations of a con layer and then passes it forward to, let's say, max pool layer. Okay, or you can put it somewhere else as well. But let's see. So
Is this kind of similar to regularization in the sense that like you're trying to control the magnitude of something?
uh, bash normalization is not. I mean, so what is regularization? It's not clear. But people don't think of this as regularization. It is trying to control the activations, not the weights themselves. So the weights of the network are weights of the network, weights corresponding to the con layer, weights corresponding to, yeah, con layer, fully connected layer are just what they are. This is just trying to, this is like a new layer with its own parameters potentially. So it's not really like imposing any restrictions on the previous weights. Okay, but it is influencing the architecture, as in the, it's literally changing the function,
Okay.
right? Going from inputs to output is changing the function. Okay, so I wouldn't think of it as regularization, but it's stabilizing the learning in some sense. Yeah.
Would you want to use regularization along with bash norm, or would that?
Regularization you can always use irrespective of batch norm. Right? So think of, so even in the code that I gave where we had manual backprop going on in the feed forward network and the logic regression classifier, I had this two norm regularization the weights, right? They were so you can always do that two norm regularization the weights of the neural network. In fact, two norm regularization the weights, and there is also something called weight decay where they change the uh, regularization coefficients. Initially, they'll put 0.01 and then they'll change it to 0.001 after some time and so on. Okay, so you do always regularize the weights of the neural network. Okay, and there's another trick which is weight decay, which we'll not to get into. Okay, but here we just want to focus on bash normalization to work with the activations, so additional parameters potentially. Okay? Not the existing weights are already there, more parameters. So the way we do it is as follows. Okay, so as the name implies, there is a normalization going on, as in some rescaling of the activations, but also there is some batch part going on. So for that, we need to recollect that in a neural network forward pass, let's say we are training, right? We don't just forward pass a single image and get the gradient with a single image, or we don't pass the all the images together and get the single last value and get the backdrop on the weights with respect to all the images. Okay, we only take like few images. Okay, which is a batch. Okay, so let's say our batch size is n, capital N. Then what I'm doing here is actually ignoring the, so ignore the previous CNN tensor pictures. For now, let's just imagine that uh, we have n different observations, so n different images. So those are the rows, and then capital D number of neurons. Okay, so it's like, let's say we had a, some output tensor. Think of vectorizing the whole tensor. It's like saying I'm gonna just stack the, I'm just ignoring the structure, CNN and all that stuff. I just put all the neurons in a row fashion. Okay, so that's like capital D number of neurons. Okay, so that's the it's like vectorized. So forget about the structures that we have seen so far. Now, batch norm is just saying, since I have this batch, okay, for a given neuron location, I know for each image what was the number. Okay, all I'm going to do is take the average of that number. Okay, take the average of that number. Average of that neuron of all these numbers of the batch. Okay, that's expectation of x. I also take the variance of these numbers. That's the, what is the variance of the numbers? How much they deviate from the expectation, right? So these are empirical numbers. Sorry, these are empirical quantities. Okay, you compute those two, and you can also have some batch norm layer parameters like some scaling of the of this numerator and some bias term in the this of this expression. See, this is a vector, right? This is a element-wise subtraction of a scalar number, right? This is a scalar, right? So I'm just subtracting element-wise some constant, which I've computed from the batch, and dividing by some other constant, and just multiplying by two other parameters, and so I get a vector again, and that's this vector here. Okay, so it's just saying whatever x I had, it's like saying take the row, the column mean, subtract the column mean, divide by the column variance, just remember that you would standardize your data set. This is how you would do it, right? That's what you're doing with some additional parameters if needed. Okay, you can think of them as one if you want, or if you can train them as well using backdrop. So that's batch norm for us. And actually, what people do is there's some so these expectations and these variance, they actually don't forget these numbers. So from one batch to the next batch, you sometimes keep a running average. In fact, I think the implementations in TensorFlow and PyTorch, they actually keep the running averages, okay, of the batch norm numbers. So it's not like this expectation is not just expectation of this guy, but also the average of these numbers and the previous numbers from the previous batches that went through the forward pass for. Okay, that's a minor detail. But batch norm is just this: some rescaling and subtraction, so that the activations. Think of these as these are the activations, right? For this neuron, they change to the activations which are low, which are somewhat like renormalized in a sense. Okay, that's what's happening. So they're rescaled. So if they're too large, then the variance term will be large, and so they'll be scaled down, for example. Any questions? And they're also zero centered, because if some numbers are positive, some numbers are negative, then let's say the expectation is zero, then negative numbers remain the same. But anyway, it's just like shifting the average value. So if all the activations are positive between 1000 to 2000, they are all shifted down between let's say between 500 to minus 500 to 500, for example. Okay. So that's all. It's just some computational trick, but seems to work well for some CNNs. For example, so here, I mean, it's also sometimes you'll see different ways of people using batch norm. Sometimes people use the batch norm after ReLU. Sometimes people use batch norm before ReLU operation. Okay, so it's just one more post processing, one more processing in between in this forward flow of your inputs to all the way to class, scores. Okay. So you'll see examples, and so you'll know where to put that. It's just a question of regularizing the activations or pre-activations. Okay? Not regularizing, sorry, rescaling the activations or pre-activations. Any questions about batch normalization? Anyway, so last trick, dropout. Okay, actually, dropout is a very interesting trick, and it's equivalent to a regularization, like W2, what is it, the weight regularization, in the sense that it somehow curtails the expressivity of the neural network, whatever. So what's the idea? So think of this one hidden layer neural network, right? So how would we train a network? We would just so for, let's say, given image, given input, which is, let's say, 3 dimensions, we would compute all the activations here, and then compute the 2 scores here. So instead of that, the idea of dropout is, think of the same scenario. Okay, every time I want to do a forward pass, remember you need a forward pass to compute the gradients, right? So for a given image, for a given input, I'm gonna first look at the neural network and knock off some neurons, drop some neurons completely. Okay, and how am I gonna do that? Just flip a coin. So like say I have lots of neurons, then I just flip coins. Coins as in like flip a Bernoulli random variable, and if it's 1 or 0, just delete that neuron as if that computation. So if you think of a computation graph, that computation is not there. Okay, I'll just randomly knock off some neurons, some computation nodes in my computation graph, essentially, and then do the forward pass and still get some scores, right? I mean, as long as I don't completely eliminate all the neurons here, I'll still get some scores, right? And then from the scores, I can compute the cross entropy loss, and I'll get CR loss. And then with that loss, I'll backdrop and only update these guys and back, because anyway these guys are not there. Their output is 0 essentially. So dropout is essentially saying dropping off these neurons in my neural network while training. Okay. So what is training, right? So I get a batch or a single data, I compute its loss, and then take the gradient with respect to loss with respect to the parameters, and update the weights, update these parameters, right? These weights over here, right? So while doing so, I'll drop some of the weights, and those weights will not be updated, and those weights will also not contribute to the output. Okay, scores. That's all. So that's all. That's dropout. And so what's the idea? So what is it doing? So it's basically it's making the network robust in some sense, or introducing redundancies into the network in the sense that even if some neurons are dropped out, you still want the remaining weights to be such that they are able to predict the output class properly. Okay. So in a sense, it wants redundancy in the network. Even if you drop off some neurons, you should predict it properly, which means that the capacity of the neuron is being used. The capacity of the neural network is being used not just to not just to learn the output classes, but also to predict the output classes in the presence of things going wrong in the other in some of the neurons, right? So in the sense that essentially you're using a smaller capacity of the network because you have to hedge for these neurons failing all the time in the training. Okay, so that's like a regularization. Whenever you restrict the expressivity of your model, then that's regularization. And so it's forcing all the neurons to be useful in a sense. And there's redundancy or robustness. That's what I mentioned earlier. And another interesting way to intuit about this is like saying, uh, so dropout is essentially saying at each time you're dropping out. So you'll actually do dropouts at every forward pass in a different way. For example, in one batch you may be doing certain dropout. In the next batch you'll again flip coins, and some other neurons will get dropped out. Okay, so that's kind of important actually, and so you can think of me training very different sub networks of these neural networks, as in like in one neural network some hidden nodes are not there, in another neural network some other hidden nodes are not there, so they're all like an ensemble. Okay, an ensemble of different neural networks, which at test time I'll figure out how to average. We'll get there, but it's like I have different neural networks at my training stage. They're not different because of course all the weights are there, but some in each network some weights are missing basically because they're not there. The neurons are not there, so the weights are not there. Okay. Um, so what do we do at test time? So okay. So I guess the first point is just not about test time, but it's just saying that. So I want to drop neurons, right? So how do I drop the neurons? If I drop the neuron with high probability, then it's stronger regularization because that means I'm dropping a lot of neurons. Okay, independently, each neuron is dropped with an independent probability with bias p. The p is closer to 1, then I'll drop a lot more, right? Stronger regularization. And then what we do at test time. So at test time, it's not like you're going to do dropout anymore. So we're not going to flip coins anymore. Okay. At test time, we'll do no dropout. But what we can do is scale the activations by the probability of dropout. Okay. This is kind of important because it's like taking the because at test time all the neurons are present, as in all the weights are there. All the weights will contribute to the scores, right? So it's like saying so here's one way to think about it. So let's say originally you had this one hidden layer neural network, okay, with this is the softmax layer weights, this is the hidden layer weights, right? This is W2 times max of this we have seen before. Now with dropout, what's essentially happening is you are essentially multiplying with a parameter p. I mean the parameter is the bias of that dropout, the coin flip. Okay, let's say p is 60% or 0.6, then your output score is like 60% of the full score, right? Is this clear or not clear? So the expression from this last but one row to the last row, all that has changed is the parameter p. So all I'm saying is, if the original full network was like this, then dropout is essentially dropping some neurons, right? So dropping some neurons, and therefore the remaining neurons compute some score. That is the output of this function. That is because I drop neurons, it's like reducing the strength of the score value. So think of it this way, right? Let's say I have 10 neurons all contributing to a score value, okay? And score is just a sum of these 10 different neurons. I dropped 40% of the neurons, right? Then there are only 16% neurons remaining. So it's as good as saying as if I had all the scores, so all the 10 neurons, but I'm taking only 60% of the values as my final score. Okay, that's effectively what's happening with the dropout. Okay. So if there is a multiplier effect like this, then all you have to do is divide by 1 by p to get back to the So here, since I'm not dropping out, I have to divide by, so since I'm not dropping out, not divide, sorry. Since I'm not dropping out, I have to multiply it by p to get to the same level as while during training. Okay, that's all.
So are you saying that this is like same for all type of applications, or
Yeah. So this is the same trick so the same thing. So while training, you did dropouts, right? At test time, all I'm saying is if you test time, if you get scores, they'll be at a different scale than the training time scores. Because the training time score at every execution, you are dropped out things. So this, let's say the scores are typically in the range of 0 to 100. At test time, since you have not dropped out, the scores may be between the range of 0 to 150. Okay. So now you just have to rescale them by just multiplying them by the probability with which you dropped out during training, for example.
so if P is 0.6, that means you're kind of dropping 40% of the neuron
During training.
training.
Yeah, and so roughly the scores are also like 40% smaller
But that would be
in terms of
random,
scale.
like they could be dropped from any of the layers.
Yeah, at random. Yeah,
So
any
your
place.
activation functions for all the layers are kind of different because that's
Yes,
if
yes,
we are
yes.
talking about vision, then the initial layers are kind of calculating edges or something. The final layer.
No, they could be doing whatever. So let's not get into that detail.
Yes, but they're
Yeah,
calculating
there are different. So each layer, if you drop out, there will be a factor. There could be different numbers here.
Yeah.
They all need to be scaled up. Yeah. So this is just for two
You
layers.
have to do scaling after each layer, or it's like one time thing that you just.
No, after each layer. It's just, it's just to rescale the numbers, okay? So otherwise your ranges will be off. This is just to undo the effect of dropout while at test time. How do you undo the effect? Either you multiply your outputs with dropout parameter, or during training, okay, you can get the scores and divide the scores by p. Okay, that's another trick. But somehow you just have to normalize the scaling of the inputs and outputs. But that's actually a second order issue. First, understand that dropout is just a way to regularize by making the neural network use its full capacity by trying to bring in redundancy into the system. Okay, so that's it. That's dropout. Yeah. So I think. Yeah, so we have seen. So I think we'll not revisit CNN. Next lecture we'll go into RNNs and text and so on. So CNNs are very good for image. So if you're going to do an image-based project, then this is a good starting point. There is actually a lot more things going on in vision actually. So like image localization and so on. We'll probably revisit some topics later. Yeah, segmentation and so on. So lots of design choices, and we saw visualizations, or how to kind of understand how well your CNN has been trained, how to do transfer learning, and then also tricks like data augmentation, bash norm, and dropout. So those are the tricks we saw. We haven't really seen optimization, which we'll see if we have time later. But of course, all this brings back to the original question of like, what is the most bang per buck? Like transfer learning is more bang per buck compared to training from scratch typically. But if you don't have that, then of course data augmentation and collecting actually data, larger data amount of data may be higher bang per buck. Collecting data has its own issues with who's going to annotate. Can I do some weak annotation? Can I just give it on Mechanical Turk or something? There are a lot of things which will actually improve your solution. Okay, as I was saying, I think in the first lecture itself, I told you that the method itself is like 5-10% of the secret sauce in a successful product. It's actually the rest of the software engineering and a lot of other bells and whistles which actually influence the success of a product or a solution. So that's it for today. And people with VPN issues and server issues, PyTorch details, yeah, you can come and meet me.
Once you told me Git bash, the remaining time that I had for my break,
Yeah.
I